Mean difference of two populations. This is also referred to as a paired comparison test, and you can see where the name paired comes in from. Now, previous hypothesis tests assumed that the populations were independent. But in this case, specifically the paired comparison test, the populations are not independent. So let's look at a situation in which the two populations are not independent. Suppose we're looking at the S&P 500 and the Morgan Stanley World Index. Now, these two groups are not independent because all the stocks included in the S&P 500 are also included in the Morgan Stanley World Index. In other words, if you have a day in which the S&P 500 goes up, chances are on that same day the Morgan Stanley World Index is going to go up as well, because usually the U.S. Capital markets make up about 50% of the world index, approximately. So how do we conduct a hypothesis test when the two populations are not independent? So the first step is we state the hypothesis. So it's still the same 4 steps that I've shown previously for any hypothesis test. We start off with the null and alternative hypothesis. So suppose that the hypothesis is that the average return on the S&P is equal to the average return on the world index. Now the thing is, in order to test a hypothesis, we need a numeric value. I don't see a numeric value there, so what we're going to do is we're going to transform that statement so that we do have a numeric value. Specifically, if they are indeed equal, then the difference between the two will equal to 0. So here's the numeric value that we were looking for. So this will be our null hypothesis, that the mean difference, that's what that says, that the mean difference between the two populations is 0, indicating that they are equal. And of course, if we disprove the null hypothesis, then we have to go with the alternative hypothesis, in that the average difference or the mean difference is not equal to 0, meaning that the means are not equal to each other. Now, the second step in any hypothesis test is the level of significance, and this will be given. And again, from previous modules, level of significance tells us how wide a band or an acceptance band we want to place around the null hypothesis. Now, why do we want to place these acceptance band around the null hypothesis? Because with hypothesis tests, we're using a sample, and samples might have errors. So that's why we want to have a confidence band around the null hypothesis. The third step is to pick the relevant distribution for this test. So long as we're testing for mean, right? So long as we're testing for means, it's going to be a choice between Z or T. But 90% of the time, the T distribution is used in order to explain what's happening to the mean, in this case, the mean difference. And then step 4, we do the test. So as we've seen in previous modules, first we set up the goalposts, and this is the acceptance band. So that's why you need goalposts. So if that's the null, we need goalposts in order to build that confidence band around the null. And but of course, in hypothesis testing, that's referred to as T-critical rather than goalpost. And to find the T-critical values, and what T-critical says is how far do you need to deviate from the null in order to have that confidence band you're looking for. So to find that T value, we need to specify the degree of freedom, which is just n-1, and the single tail area. And n in this case represents the number of paired observations. So for example, if you're looking at the two indexes over a 12-month period, that would be a total of 24 return observations, but only 12 return differentials. Because what you're doing for each month of the 12-month is you're just finding the average difference. So you're going to have, over a 12-month period, you're going to have 12 differences. So you'll have 24 individual returns because you're looking at 2 different indexes, but you're finding the difference between these individual returns. So you'll only have 12 differences during that 12-month period. Now the next step is to determine whether the sample falls within the goalpost or outside the goalpost, because if the sample is within the goalposts, then we accept the null, right? So going back here, so it's all a matter of where does the sample fall. If the sample falls anywhere here within the band, we go with the null hypothesis. But if the sample goes anywhere outside of that acceptance band, then we go with the alternative. So you see, this is why we need to find out where the sample lies relative to those goalposts. And that's what sample statistic is, or test statistic. Now, what I always like to do is I like to use a ground-up approach. So instead of just saying, here's how you find the t-stat when you're doing a paired comparison test, I like to start off with our most basic framework for finding sample statistic. And what sample statistic says is the following. How far did the sample deviate from the hypothesized value measured in units of standard errors? That's it. So then how do we tweak this for a paired comparison test? Paired comparison test. So we're looking for the average difference. So rather than just looking at the mean, like a population mean, we're looking for the mean difference between the populations. And we compare that with the hypothesized, there you are, the hypothesized mean difference. And rather than looking at the standard error of the sample mean, we're looking at the standard error of the sample difference, right? So the whole point with this particular hypothesis test is we're measuring the difference between two populations, and that's it. That's it, ladies and gentlemen. So let me ask you something. Are these two different frameworks, or is it just one framework? The way I see it is just one framework, but that's just being sort of modified because the context is different. All right, so let's proceed. And as I indicated, this here represents the sample mean difference, so that's what we're looking at. And this would be the standard error of the difference, so standard error of the sample difference. And again, what we do here is it's calculated the same way standard error of the sample mean. We look at the standard deviation of the differences, and then we divide it by the square root of n. And again, the rationale for dividing it by the square root of n is as follows. The larger the sample size, the less errors that are associated with the sample. And then what's the decision rule? If the sample stat falls within the critical values, we accept the null. And again, I use this goalpost and penalty kick analogy, and it's the same thing. So if if the ball falls anywhere inside the net, it's a goal. It's the same thing with hypothesis tests. If the sample falls anywhere within the critical values, we go with the null. On the other hand, if the sample falls outside of these critical values, doesn't matter which side. Could be on the plus side or minus side, doesn't matter. If it comes outside of the goalposts, then we would reject the null, and therefore we would go with the alternative.